So a lot of people think, oh, is this gonna replace everything? Is this gonna replace everything? No, I don't believe that hydrogen is gonna be the replacement for fossil fuels. I think that hydrogen is going to be part of the solution, right? Part of the solution to get us off of our dependence on fossil fuels, right? Again, that's going to include all of the other renewable energy technologies that we have available to us, because our reliance on fossil fuels is so strong that in order to replace it, or even to displace our reliance on it, right, it's going to take a lot of additional technology. It's going to take a lot of research. It's going to take a lot of additional things in order for us to shy away from that.
Alpha Day, it's your innovation coach, Rob Jackson, and welcome to another edition of the Innovate Guam podcast, the podcast where we explore all things innovation, technology, and improvement related to the island of Guam. Don't forget to like, subscribe, and follow me on YouTube, Facebook, LinkedIn, Instagram, and Substack. My podcasts drop at the beginning of each week. Also, be sure to check out my Innovate column in the Pacific Daily News the first and third Fridays of every month. All right, I'm very excited today. Our guest for today's episode is at the very center of one of Guam's most exciting clean energy research efforts, turning our surrounding ocean into a source of hydrogen fuel. Here's some highlights on his background. He is assistant professor of chemistry at the University of Guam. He's a proud Triton Global Scholar, lead investigator on the UOG PNNL hydrogen from the Seawater project. He's focused on seawater electrolysis challenges, and he's a builder of Guam's future clean energy workforce. He's active in UOG's chemistry and STEM community. Ladies and gentlemen, I give to you Dr. John Limtiaco. Doc, how are you doing?
I'm doing great. Thank you for inviting me on your podcast. I'm excited to talk about this science that is taking off, science that is super interesting to the community, super interesting to the University of Guam. It focused on performing electrocatalytic conversion of seawater to generate clean energy sources like hydrogen and ammonia and things like that.
Outstanding. So we're excited to hear about all of that. So before we get into that, we have a tradition here on the podcast. We start off with some icebreaker questions to get a sense of where your head is at in terms of innovation. So tell me, what is your definition of innovation, and what does innovation mean to you?
I believe innovation is the work that we do to conceive, develop, and scale up technologies that benefit myself, my community, the students that I teach at the University of Guam, but more so to move forward our community, right? To lift up our community, to progress in science, to progress in everything that we do.
Outstanding. So you got your undergraduate degree here at University of Guam, and then you went off to school. Can you talk about your time when you went off to school? Where did you get your advanced degrees from?
So I'm a product of Guam. I grew up on Guam. I went to Mooney Elementary, Agata Johnston, George Washington High School, graduated, decided to stay on Guam for my undergraduate degree, got my bachelor's in chemistry at the University of Guam. One of the first projects that I did here at the University of Guam was investigating the arsenic speciation of groundwater on Guam. So that got me my first publication my professor at the time, Dr. Michael Vuki. Following undergraduate education, I decided to go off island to pursue my graduate degree at the University of California at Riverside. There, I worked with a faculty by the name of Cynthia Larive, who actually had her own analytical
Yes.
instrumentation lab. And
And she's a daughter
I
of
was able to
Guam, right?
secure a grant through the U.S. Pharmacopoeia, and that grant led me to investigate heparin and heparin oligosaccharides using NMR. So, I'm going from biological relevant molecules that are used in drugs to actually doing seawater electrolysis investigations now. So it's a huge step in another direction for what I'm used to from graduate school.
Talk to me about what drew you back to Guam. I mean, obviously you went off, uh, left the island to pursue advanced education. A lot of our young people, particularly those bright and shiny young people, they go off the island and there's not really anything drawing them back. What drew you back to Guam to do this kind of work?
Well, when after I got my graduate degree, I decided to do a postdoc at UCSD, and there I focused on doing research on biodiesel. Right, so we would take, for example, waste diesel or or oils derived from different sources, and we would convert it into biodiesel. And I thought to myself, well, this is something that might be interesting to perform on Guam because we have a lot of waste crops that are not used. Maybe we can isolate the oils, the lipids, and things like that, and then convert them into biodiesel and then use them as, for example, a useful industry. So that was one scientific question I had when I came back to Guam was, how would that research look on Guam? Can we actually incorporate that into as a potential source of revenue for the island? Another thing that drew me back to Guam was, again, family. I went off to graduate school. My family stayed on Guam. I decided to come back and be happy here. So I came back for family. I came back to teach at the University of Guam. I always knew after graduating from the University of Guam that I wanted to come back and return to the community that was that brought me so far, that set me off to do this graduate degree, that set me off to work on these interesting research projects. I knew I wanted to come back here and do the same for the community that I grew up in. So that was another drawing factor back to the University of Guam, was to teach at the university as a faculty member here.
Innovation leaders, it's your innovation coach, Rob Jackson here. Are you ready to elevate your vehicle fleet operations? Fleet Solutions is an AI-enabled fleet management system. Fleet Solutions provides real-time video, smart analytics, and total efficiency. Keep your people safe and keep your business moving forward faster than ever before. Fleet Solutions, arriving tomorrow, today. Visit thefleetsolutions.net or call 671-988-9748 to schedule your personalized demo and revolutionize your fleet operations today. So tell me something that you would want young people to know about careers in science, technology, engineering, and math, the STEM fields. Because a lot of times young people might have a vision of the STEM fields as something boring or hard or difficult, or that's not for me kind of thing. What would you say to those young people to encourage them or share with them something that they might not know about work and pursuing the STEM career fields?
Personally, I believe that the progress that you make as an individual in science is worth the work that you put in, right? So making those discoveries, publishing those papers, getting that sense of accomplishment through the work that you do in the lab, the work that you do in the field, that helps to overcome the hesitance that I had, for example, when going to STEM. Um, a lot of students that come to me and they talk about what they want to do in the future, they're concerned that they're not ready, right? I'm not ready. I wasn't
Yes.
prepared enough. uh, how successful am I going to be in pursuing this career in STEM when I don't feel like I'm ready? But I'm going to tell those students that no, you are ready. You've come from a background. You may have to work on it a little bit more. You may have to put in more time, but you are what the future of science is, right? You are the future of science. Just because you may not have the same background that other students have doesn't mean that limits your ability to participate in science and be successful in science. What you bring to the scientific table, to what you bring to scientific knowledge is worth all that experience that you had in the past. What you bring to the table expands it. It makes science a more diverse field that you're going to find success in.
You know, people see chemistry as one of those hard subjects, one of those difficult subjects, but you were not deterred. You jumped right into the chemistry curriculum at the University of Guam. You know, what was the difference maker for you jumping into that challenging undergraduate curriculum?
For me personally, it was the satisfaction of understanding the expressions that came with the science, right? So a lot of times when I teach, for example, general chemistry, I give the students a lot of these expressions, these equations. And a lot of students think, oh, I have to memorize these in order to be successful. But I
Right.
tell my students, no, you should be able to derive these expressions because, again, they all come from some fundamental physical basis, right? All these expressions that we use, all these equations that we use have some fundamental basis that are simple to derive. So my transition into chemistry, because originally when I went to the University of Guam, I was a biology major, as most students are when they come to the university. I was a biology major. I was interested in biology because I did a lot of biology in high school. But when I came to the University of Guam, I found this whole realm or this whole new world of science that was actually more interesting to me than biology, and to understand the basis, to understand the foundation of that science is what really drove me to pursue that degree in chemistry. I didn't want to know, oh, this is the expression. I wanted to know, how was this expression brought about? What does this expression
Mm.
mean? What does every single term in this expression mean, so that I understand what I'm trying to solve? And that ultimately that's what led me to pursue a degree in chemistry versus my original plan, which was to pursue a degree in biology.
Okay, okay. So, Doc, before we get into Seawater and the UOG project, let's ground our listeners in the big picture of hydrogen as an energy source or an energy option. You know,
Mhm.
for our audience who isn't steeped in energy policy, how do you explain hydrogen as an energy carrier?
So, uh, so if we consider potential sources of energy, right? We all know fossil fuels, petroleum-based fuels, are what our civilization is built on, right? Gasoline in our vehicles, the diesel that runs the generators here on Guam to generate electricity. Our entire infrastructure of energy is petroleum or fossil fuels. However, hydrogen makes up a huge portion of all the matter on Earth, right? Hydrogen makes up a huge portion of all the matter on Earth. When we consider, for example, hydrogen as one of the two atoms or one of the two components of seawater, right? You have
Right.
oxygen and you have hydrogen. If we can use the hydrogen in seawater and we can extract that hydrogen, can we use that hydrogen to, for example, generate electricity? Can we use that hydrogen to propel your vehicle forward? Can we use that hydrogen to to move ships through the ocean? So that's the basis of this research. Can we use an element that is present in a huge abundance on Earth versus something that we have to that was produced millions of years ago, that is buried under the soil, that we have to dig up? Can we use something that is readily available to us as a fuel source? And at this point, we considered it unlimited, right? We consider the amount of water on Earth, though it's not clean, purified water, amount of water on Earth would be an unlimited supply of energy if we can just
Yes.
extract that energy carrier.
Yes, yes, great, great possibilities. So that might answer part of my next question about why so many countries are excited about hydrogen and moving forth. Can you talk about kind of some other work that's going on that's maybe high profile, not just here on the island, but other places that are looking into hydrogen as a fuel source?
So my research is grounded in using seawater as the feedstock for hydrogen production, but a lot of research is going into not only generating hydrogen gas, but generating other potential energy carriers, right? So I mentioned ammonia. You could also generate other value-added products like formic acid from electrocatalytic conversions. Um, Again,
Which is
water
used, formic
is
acid is used in what?
formic acid is used in as a source for let's say a carbon generation experiment or carbon generating large molecules from smaller, simpler molecules, right? So formic acid is a very small, simple carboxylic acid that can be used to generate larger chain hydrocarbons or other things that require these carbon based backbones.
Okay.
Yeah. So getting back to global need for hydrogen again. Not everywhere, not every place has a source of fossil based fuels, right? A lot of places have to import it, like Guam, and it could be quite costly. So can we use non-potable sources of water? And other countries are also investigating. Can they use their non-potable sources of water to generate energy? Right? Can they generate hydrogen? Can they generate these other energy carriers that can be used because they don't have the petroleum or the fossil fuel based infrastructure necessary for them to be self-sustained?
Yeah. So I really like the fact that you emphasize non-potable water because there's social implications of deriving hydrogen from water as a energy source when a lot of areas of the world right now are, having facing water scarcity kind of issues. And of course, water is essential to human life, and you don't want to generate one problem by another problem by saying, okay, we're going to get our hands on every source of water we can and generate energy from it. It would be nice the water that we can't drink right now to use to sustain human life,
Mm.
get hydrogen from that as the energy source.
Correct. So yeah, there's a huge social implication, right, of using clean water when many places are undergoing drought, when many
Yes.
places have the inability to get clean water. Is it socially responsible to use that to generate fuel? Which again, if I was to generate fuel from clean water, the cost of water would skyrocket. Right, it's like any
Yes.
other source of energy, right? If, for example, when farmers in the U.S. were converting their crops to corn to generate ethanol, right?
Yes.
It was a
Yes.
huge social dilemma. Do they generate food, which is cheaper than fuel, where they were going to get more money from? So again,
Yes.
you know, of course, if a farmer is going to say, no, my trade-off would be I want more money. I want to generate a crop that gets me a greater income. But that creates that social dilemma in what is socially responsible, and the socially responsible thing to do for hydrogen would be to use again a non-potable source of water versus purified water that we would pull up from our aquifer, or water that we would pull from a lake or a river.
Yes. Yeah. Public policy, the implications and the second and third order effects of public policy playing itself out in broad daylight.
Mm.
So let's talk a little bit. When hydrogen is produced via electrolysis, powered by renewables, what are the main environmental benefits that you see from there, especially in terms of greenhouse gas emissions, local air quality, and those kinds of things?
Mhm. So with respect to using renewable fuels to generate hydrogen, that's the optimum thing to do, right? We can use solar power, we could use wind, we can use wave technologies to generate hydrogen by again providing the energy necessary for the electrocatalytic separation of water. When we consider, for example, solar power, right? Solar power is only available to us when the sun is out. And we know, living on Guam, right, having solar power on our solar panels on our roof, having solar power paneled farms on Guam, there's an overabundance of energy generated during the day. Okay, so much so that I think that there was concern from our public utilities that, hey, we need to start putting battery storage systems. We need to start using
Yes.
battery storage systems to store all this extra energy that is being generated during the day, so that we can then utilize that energy in the evening, right? So
Yes.
so another plan would be to use that energy, that excess energy that is not stored in batteries, to generate, for example, hydrogen gas that can be stored in cylinders by generating, or it could be liquefied, or generating other, again, energy carrier molecules that can be stored and maybe more easier to store than hydrogen gas, so that, let's say, in the evening, or when the sun is not as intense, we can use those sources of fuel to generate electricity through using a hydrogen fuel cell, or even direct combustion of hydrogen or other components.
Yeah, I really like that explanation and the discussion of how all of the renewables can work together. So, you know, hydrogen um, and energy storage and balancing that with intermittent renewables like solar, maybe not so much wind here on island,
Mhm.
but
Yeah.
wind other places
Mhm.
really can help out in a whole energy portfolio, if you will, to solve humanity's needs. So,
So,
really excited
well,
about that.
so yeah, so a lot of people think, oh, is this gonna replace everything? Is this gonna replace everything? No, I don't believe that hydrogen is gonna be the replacement for fossil fuels. I think that hydrogen is going to be part of the solution, right? Part of the solution to get us off of our dependence on fossil fuels, right? Again, that's going to include all of the other renewable energy technologies that we have available to us, because our reliance on fossil fuels is so strong that in order to replace it, or even to displace our reliance on it, right, it's going to take a lot of additional technology. It's going to take a lot of research. It's going to take a lot of additional things in order for us to shy away from that.
Right. So let's talk about some of the cons and challenges now. What are the biggest drawbacks or technical challenges with hydrogen today? You know, cost of production, storage, transport, round trip efficiency, safety concerns that some people have. Can you talk about kind of the drawbacks with hydrogen that exist today?
So I believe the primary drawback for hydrogen right now is, again, the feedstock, right? So how are we going to produce the hydrogen? What sources of water are we going to use to produce it? Again, that not only leads to, having clean water, but also the production of byproducts that are not so great for us, right? So, for example, in an acidic environment, a major product of, for example, seawater, or electrolysis, where there's a high chloride content, would be chlorine, which is a toxic gas. So also the production of hydrogen can be quite problematic, right? If you don't know how to store it properly, or if you're not careful, right? Because hydrogen is a highly combustible fuel. It's extremely explosive. So in that facility where you're producing hydrogen, for example, there has to be a lot of safeguards to ensure that you don't have a sufficient amount of hydrogen building up in that facility, where a single spark could bring that place to combustion. So there's safety implications with respect to that. There's safety implications with respect to transport, right? So early on, I believe it was in the early 2000s, there was a huge push for hydrogen vehicles. But one of the big concerns with hydrogen vehicles was, how do we store hydrogen in the vehicle? If the vehicle gets into an accident, do we expect that the vehicle to blow up, right? So with new advances, with new engineering, that's not so much of a problem now, right? They have the storage capabilities to store hydrogen in an environment, in encasing, to prevent there to be any significant damage if the vehicle is experiencing a crash or something like that. So those were challenges earlier on. They're not challenges now, but there's a lot of challenges with respect to transporting even today, right? Do we transport it as a high pressure gas? Do we transport it in a cryogenic form, in a liquefied form? And all of those come with difficulties and challenges as well. But again,
Yeah.
the trade-off is the trade-off with that is, we have these difficulties, we have these challenges, and every day we're making advances to improve, to accept that technology, to improve on that technology so that we can use the technology. Again, with using fossil fuels, we understand that as we burn fossil fuels, we're putting carbon dioxide and other hazardous gases into the environment, and it's something that we have to contend with, right? Are the advantages of using hydrogen and the cost associated with hydrogen, do those outweigh the implications or the problems that are arising because of our dependence on fossil fuels?
Yeah, so one of my previous guests on the podcast was two gentlemen. Serge Markov was the CEO of a company called Sea Cheetah, and his director of business development and logistics, Greg Lewis. And they have a hydrogen-powered, basically flying boat that they're marketing. And they were talking about all the advances in safety that really were derived from Toyota Motor Company about how to store hydrogen in a safe and effective kind of way. And then you talked about, um, all of the different considerations about the distribution and logistics of that fuel now, and what form do you store it, and what form do you uh, uh, distribute it, and low volumetric energy density, and all those kind of considerations, high pressure and cryogenic storage kinds of issues and stuff like that. And it was kind of interesting how this kind of comes back full circle in this discussion as well. Yeah.
Mm.
Let's talk about um, globally right now. Um, how big is the hydrogen market today? How big would you say it is right now? I know it's in its infancy, but
Yeah.
right now, how big would you say it is?
I can't give you an exact number, but I would say it's quite small, right? You could go online and you would find some major companies like Hitachi, Siemens, also BP Energy that are putting some investment into hydrogen technology, right? So Siemens is and Hitachi are promoting some of their hydrogen production plants, some of their infrastructure into the market. So it's not well developed, but I would say that it's moving forward, right? It's progressing at a rate where maybe in a couple of decades it may become viable, it may become something that is truly changing the energy infrastructure of the US and worldwide as well. So I would say it's really quite small. There's still a lot of research going into it. There's still a lot of things that need to be understood about using hydrogen as a replacement, as a fuel source that needs to move through its proper cycles and so forth.
Understood. So let's talk about it. I know we're going to transition kind of later on into the specifics of your research there at the university. But what are kind of the major scientific or technical challenges to getting where we want to go with using hydrogen more widespread as an alternative fuel source? What are those top scientific or technical challenges that exist right now um, as barriers?
So my research is quite focused on seawater electrolysis, and the major problem for seawater electrolysis, again, based on what I'm familiar with, all the research that I've done, reading the articles, it's developing robust catalysts, right? So generating robust catalysts to produce the hydrogen fuel, or to produce that hydrogen energy carrier. So a lot of times the catalyst can be poisoned by products of the reaction. A lot of times the catalysts have a finite lifetime, and these catalysts can be quite expensive. So when I'm talking about catalysts, it's the surface at which the reaction occurs. So a lot of the research that I do, a lot of the papers that I read are in the development of the catalysts in order to improve the production of these fuels, right? In order to improve the ability for electrons to move between the metallic surface and the actual molecules that are necessary to be transformed for that fuel to be produced. So
So, Doc, let me stop you and let you break down the catalyst because I think that's a very important concept. Can you put it in layman's terms and make it understand what is so important about the catalyst, what exactly it is in layman's terms, and talk about that for a little bit?
Okay. So when we define a catalyst is simply some substance that lowers an activation energy barrier in order for a reaction to occur, right? So if we assume that reactions occur only under conditions where there's sufficient energy to drive that reaction, that's how a reaction occurs. There has to be a sufficient amount of energy in order to drive the reaction to formation of a product. That energy is typically, the energy required to drive that reaction is typically some energy that's over some activation energy barrier. So it's some energy height that that system has to overcome in order to go from reactants to products. A catalyst is a substance, or it's something that helps to lower that barrier. So what the catalyst does is it lowers the barrier that's required, or the energy barrier that's required to go from reactants to products. So
Yes.
the reaction to generate hydrogen as a fuel has this activation energy barrier. And what we do is we take a metal, and what the metal does is it places the molecules on its surface, and it allows electrons to move back and forth between the molecules. So it provides basically a scaffold or a platform for the reaction to take place, because ultimately the reaction that we're interested in is a reduction oxidation reaction. It's a redox reaction where electrons are moved from one molecule to another. So that metal surface provides the basically the support for the molecules to interact with, so that electrons can move back and forth between the molecules that are reacting.
Yeah. So, what kind of metal sources are you using in your electrolysis
So
experiments?
because our research is fundamental, it's understanding the fundamental science. We're using a platinum catalyst, so it's basically a platinum metal
Platinum.
that serves as this catalytic surface for the reaction to occur. But again, because our research is only focused on understanding the reaction, the chemistry of that reaction, and not really focusing on catalytic development, we're just using a platinum. But a lot of times we're just using platinum. But a lot of groups, for example, in China, a lot of groups in the US, a lot of groups in other countries who are doing hydrogen, energy research, they're focusing on how can I modify this catalytic surface, this metallic surface, in order to drive the formation of these hydrogen or of these energy carriers.
Okay. All right. Before we transition to the meat of your research, can you talk in terms of framing the um, the explanation of the prospects of hydrogen as an alternate fuel source to a policymaker or community leader? Basically, the simplest way to summarize the realistic promise of hydrogen and its pitfalls that we need to avoid. How would you do that if you were talking to a policy maker or leader on that?
Yeah, so again, it all gets back to our reliance on fossil fuels is going to be difficult to overcome. And one technology is not going to be the be all end all, right? So it would be nice if one technology was the be all end all for petroleum fuel, right? So again, it would be nice to displace that, but it's not going to happen with one technology. So hydrogen is a technology that's going to help supplement solar. It's going to help supplement wave renewable energy technologies to curb our complete reliance on fossil fuels. right? So ultimately, that's what I want to get across is hydrogen is not in itself going to be the be all end all, right? I don't see hydrogen as supplanting solar or supplanting wave energy technologies. I see hydrogen as a way to store the energy so that we can use it at a later time. We can store the energy, and hopefully with at some point it has the potential to also be used to for our vehicles and so forth. But at the moment, I see hydrogen as a way to store energy so that it can be used for energy production when other sources of renewable energy are not available to us.
All right. All right. Let's now zoom in on the work that you're doing there at University of Guam.
Mm.
Can you talk to me about kind of the origin of UOG, PNNL collaboration to generate clean energy from the sea? How did that first come about, and kind of what's the history of that project and working together?
So it's a funny story. So University of Guam, the administrators of the University of Guam send out invitations to jump into meetings when they're talking to potential collaborators, right? So I received this email from the Office of Research and Sponsored our Office of Research and Sponsored Programs to, hey, you know. PNL is working with GPA on a project. They're interested in maybe bringing on some University of Guam researchers to assist. So I was like, okay, that's awesome. Let me jump onto here. I have my degree in chemistry, though I never dealt with whatever generation method they were talking about at the time. I'm a chemist. I might have some insight. I might be able to contribute. So I jump on this call, and funny thing is one of the individuals on the call was the brother of one of the faculty members I had at graduate school. So one of the directors at PNL, or one of the lead scientists at PNL, he was the brother of my NMR instructor at UC Riverside. So I noticed his face and I was like, wow, this guy, he looks really familiar to me because they look very similar. And I asked him if you're the brother. He goes, oh yes, I'm his brother. And I was like, wow, it's been a while, but it was awesome meeting him. So only to find out that there was really no project that the university can contribute to. PNL wanted to do a separate project with the University of Guam, which was separate from GPA. So I went into the meeting thinking that, oh, I'm a university researcher. I'm going to assist in a project between PNL and GPA on something they're doing. But ultimately, it turns out that PNL was interested in doing another project with an institution on Guam, and they selected the University of Guam to do that. And they were able to match me up with scientists at PNL who helped me write up a proposal that we submitted to the Department of Energy to bring funds to Guam to do this research.
Awesome. So for our audience members, can you talk about who PNNL is, what's their background, what they bring to the fight, and why that was so important for Guam?
So PNL is a national laboratory that's located in Richland, Washington. So their main focus is on energy security, but they're also one of the major national laboratories that have to deal with chemistry. Um, they have their facilities is quite expansive. They deal with a huge realm of different research. Their portfolio of research is huge, from cybersecurity, to simple basic science, right? So what we do is we collaborate, and we're in fact taught by the researchers at PNL on how to do the science that we're doing here on Guam. So they're the experts. uh, During the summer, we go there for 10 weeks and we participate in the research that they're doing. And then when we get back to Guam, we continue the research here, right? So the research that we do there helps to build on the research that we're doing here. They explain to us the fundamentals of the science. We talk to engineers. We talk to, for example, modeling scientists, physicists on what's actually happening on the platinum surface, right? How do we account for the energies associated with this molecule interacting with the platinum, and is this interaction preferential over this molecule interacting with the platinum? And again, what we're doing is we're saying, okay, this is the this is the energy information that we get from the modeling. Does it match what we see in the laboratory? If I were to perform this experiment, does the energy change associated with this reaction make sense based on what the physicists are telling us that this energy attributed to this reaction should be? So that's where the major science is occurring at PNNL, because they have the facilities, they have the scientists who understand what in fact is going on. Here, what we do here is we try to bring that information to Guam. We teach that to the students. We try to carry on the research, right? Continuing on in the laboratory, continuing to talk to those modeling scientists, trying to understand what's in fact happening with our experiments in the realm of seeing what's happening at the individual molecular scale.
Yes, yes. So for the listening audience, PNNL, Pacific Northwest
National
National
Laboratory.
Laboratory. And again, one of many of a portfolio of the nation's national laboratories who are working on cutting edge scientific work to advance technology and stuff like that. So
Correct.
you're talking about cutting edge type stuff with some of the tip of the spear kind of scientists
Yes.
out there right now. So
These are the
let's talk
scientists
about,
that come, the major researchers in the US. These are scientists who are considered major researchers in the US, right? So they're working at a national laboratory, getting funds from the US government to perform research to advance the science of the US, right? To keep the US at the
yes,
forefront of scientific innovation, keep the US at the forefront of scientific achievement, scientific discovery. These are the individuals that we work with at PNNO. And it is such an honor to be able to work with these individuals to address the problems that we see on Guam, to address, you know, what we see on Guam as major hindrances for us to be. I apologize for that. I'm right next to a laboratory, so it sounds like they just dropped something. But so we're working with PNL to move forward, you know, alternative energy science here on Guam, and to become, you know, we're trying to become the hub of renewable energy science here in Micronesia. Because again, we see that as the role of the University of Guam. The University of Guam is the hub of science in the Micronesian realm, and
yes.
that collaboration is helping us to move that forward.
Can you talk a little bit about the students that you have working on this project with you? Because I would think that is just incredibly exciting for a young student here on island to get a chance to actually participate and work in on this project that is like cutting edge science and stuff. Can you talk about how they got the opportunity, how you picking those students to be part of the project, and what kind of things that they're doing and what kind of opportunities they have?
So the students that we've had so far, we put out a invitation to apply. The internship opportunity, the project comes with a stipend, so the students are paid during the semester to participate in the project. They get an additional stipend when they go to PNL for 10 weeks. So when they go out to PNL, we provide housing, we provide stipend for them to purchase food. We accommodate them out there. They work with the scientists. Then when they come back again, they're provided additional stipends to continue to work throughout the semesters. We select the students off of a simple application. We put out the announcement that we're looking for students to go to PNL for the summer. We typically get, you know, in the range of like 10 to 15 applicants per announcement. Of those 10 to 15, we select about 5 students to participate. The reason we select 5 students to participate again is we're limited to the amount of researchers that are available at PNL to facilitate the research of the students. They do have their own projects they have to work on, so they can't just stop their project to work with us on our project. They must continue on their project while also working with our students. So
Right.
so again, we try to limit the amount of students that go out to help the researchers out there continue their progress while also working with us. Um, We go to P&L. They work out there with the scientists. We select them using a simple application. The students that we've selected so far, I would say, we had 3 engineering students so far that went through the P&L experience. We have um, one math major. We had one math major who worked with an engineer last summer to do the molecular modeling things with the physicist. That was pretty interesting, learning how to do all that fun stuff. We had one biomedical student who is still currently in the program, and we have 3 chemistry majors who are currently in the program.
So a
So again,
diverse group of folks. Yeah.
a very diverse group of folks. Not only chemistry, biology, math, and engineering.
Outstanding. So let's circle back to what you mentioned about the Department of Energy grant that you were successful at. Can you talk about that Department of Energy grant? What is it? What's the name of it? What's special about it, and any other key people or institutions that were helpful in getting the funding under that grant?
So the Department of Energy grant that we had is no longer under the same umbrella. It was originally it was through the Department of Energy Office of Science. It was an Office of Science grant that was given to University of Guam and P&L in order to do the research. The grant was titled Basic Energy Science: Reaching a New Energy Workforce. So it was BES Renew. That program was phased out with the new administration, and our research now falls under the umbrella of EPSCoR. So it moved from being a BES Renew project to now an EPSCoR project. So we
Okay.
fall under the umbrella of the EPSCoR group of projects. So the project again was tailored on bringing a new science to a region where the science was not developed, right? So a region where the science is novel. And that science was to be built in collaboration with the national laboratory, and it was focused, or it was tailored to attract schools that are non-research R1 institutions, right? So Guam is a non-R1 institution, meaning that we're not a complete research institution like a University of California school would be, or Harvard would be, or MIT, right? We're basically a research institution whose primary focus is on education. So
Okay.
the grant was tailored to schools like the University of Guam, where we can collaborate with a national laboratory to bring a relevant science here based on some project that we propose.
Okay. So at its core, what is the main scientific or technical problem that your project is trying to solve about seawater electrolysis?
So the core of our understanding is, does the organic composition of seawater help to promote the catalytic splitting of water? So do the organic components that are present in seawater, though they may be minute, very minimal, do they help to promote the electrocatalytic splitting of water? And again, do those organics help to protect the electrolytic surface from, for example, the hypochlorite generation reaction that is competing with the reaction of interest to us? So do those organic molecules help to limit the chloride ion from interacting with the platinum surface? So what we're doing is we're running a series of experiments where we take model seawater, we spike it with simple organic molecules, and we look at the electrocatalytic profile. Does the electrocatalytic profile, does the CV, does the LSV change as I introduce these organic compounds, and do they change at specific concentrations?
Right? So you hinted at this before, but I'm going to bring it back. What's so complicated and difficult about splitting seawater into hydrogen and oxygen? What's the difficulty in doing that?
So the primary difficulty in splitting seawater, or using seawater as a source as a feedstock source for hydrogen production, is the high abundance of chloride ion. So chloride competes with oxygen in undergoing an oxidation reaction, and it can outcompete oxygen, though it's not thermodynamically favored, it's kinetically favored. So in the oxidation reaction, there is a 2-electron transfer for the formation of hypochlorite versus a 4-electron transfer versus in the oxidation of water to produce O2. Right, so kinetically, the reaction is favored to form hypochlorite versus forming oxygen O2. So that's one of the challenges. The other challenge is water or seawater is not a simple medium to perform a reaction. It's a very complex medium containing a wealth of different organic biological components that may interfere with the reaction at the catalytic surface, right? A lot of things, in addition to water, will interact with the surface of the electrode. And some things may have a preferential interaction with that electrode than water does. So we have to understand, in addition to the chloride interacting with the surface and the oxygen interacting with the surface and the hydrogen interacting with the surface and the water interacting with the surface, are there other things that are interacting with the surface that would inhibit the efficiency of this catalytic transformation? So those are all the things that come into attempting to understand the difficulties of using seawater as this feedstock for hydrogen production. There are just so many things in seawater that can outcompete with this reaction, but the reaction that we're interested in is this one simple reaction.
Yes. So kind of walk us through what is actually happening at the cathode and the anode when you run an electrolyzer on seawater. When you're doing that, performing that experiment, what actually is going on?
So we have a reduction reaction at the cathode. So reduction defined is a loss of, or I'm sorry, reduction is the gaining of electrons. So something that is reduced is gaining electrons. And at the anode, we have an oxidation reaction. The definition of an oxidation reaction is the loss of electrons. So a reduction reaction and an oxidation reaction does not occur in the absence of each other. Something must lose electrons and something must gain electrons. So in our electrochemical cell, we have a cathode and an anode. At the cathode, we have a reduction. At the anode, we have an oxidation. In simple water electrolysis, right? So if we just take clean water, we put some ionic compound in there in order to generate an electrolytic solution, right? Because it has the reaction can only occur in an electrolyte. So we could put something like potassium hydroxide or something that would dissociate to form ions. So in a simple reaction where we don't have chloride, right? We have two water molecules interacting with the cathode surface. Those two water molecules gain electrons and they produce hydrogen gas, right? So we have two molecules of water gaining 2 electrons in order to produce 2 hydrogen gas, in order to produce 1 molecule of hydrogen gas and 2 hydroxide ions. So that's the simple reaction that's occurring at the cathode surface. At the anode surface, we have 4 hydroxide ions losing 4 electrons to produce water and 1 molecule of oxygen gas. So that's happening at the anode, right? So we have 2 reactions occurring. Both reactions involve the transfer of electrons. The water is gaining electrons in order to produce hydrogen gas and hydroxide ion. The hydroxide ions are losing electrons in order to produce water and oxygen gas. So that's occurring at the anode. If there is a high chloride concentration, the chloride ions are competing with the hydroxide at the anodic surface, right? And are again being oxidized. They're losing electrons, and in that process, they generate hyperchloride. Depending on what the pH is, they can generate hyperchlorite or they can generate chloride or chlorine gas. So those are the reactions that are occurring at those 2 surfaces.
So walk us through kind of what your main objectives are with the project, where you are in achieving those objectives or the project itself, and how would you judge your progress thus far to achieving the goals and objectives you're looking to achieve?
So currently we are again working. So Working with undergraduate students is different than working with a graduate student, right? We have to work around the student's schedule. They have a whole bunch of classes they need to take. I have a whole bunch of classes I need to teach. So again, we're working around each other's schedules in order to accomplish the goals of the project. So currently, I've had 4 students present at national conferences on the research they're doing. So that's a huge
Yeah.
a plus of promoting the science here, of getting this new workforce engaged in the science, right? So I've had 2 students present at SACNES, and the University of Guam just put out a news article about the participation of our students in SACNES. I had 2 students participate in SACNES last year, and I had 3 students participate in SACNES this year. So I had a total of 5 students successfully participate and present their research at the SACNES conference. So each of those students had a small portion of the project. So for example, in the first summer where the student presented their research, we were focused on actually just performing the experiments, understanding how to set up the electrochemical cell, how to set up the appropriate parameters to perform the experiment, and whether or not we can translate that information or those procedures to the instruments that we had on Guam. So the great thing about the grant is it provided us money to purchase the equipment that PNNL has in order to do the research here. So the electrolyzers that they were using at PNNL are the same electrolyzers they're using here at the University of Guam. So that allowed us to purchase the equipment, to purchase the electrochemical cells that they're using there, so that the transition from PNNL to Guam was as seamless as possible. It was easy. It was easier for us to use the parameters that we developed while we were there and incorporate it in the instrumentation that we have here. So in the first summer, we were focused on really understanding how to set up the electrochemical cell, how to perform the experiment, how to interpret the data set. And what that was focused on was on the cathodic reactions. We were focused on what's happening at the cathode. Not really concerned about the oxidations that's occurring at the anode, but what's happening at the cathode. We were focusing on that. In the second summer when we went out, right, we focused more on molecular modeling and also understanding the reactions that are occurring at the anode. So in the first summer, we focused on the cathode, setting up the electrochemical cell, understanding the hydrogen evolution reaction, and measuring the potentials and the currents associated with that reaction in different sodium chloride or in different model seawater samples. So when I say model seawater, basically what we did is we took purified water and we introduced different levels of sodium chloride in it as a mimic to the salt content of seawater. So we introduced different levels of sodium chloride to mimic the different levels of salinity that we would find in seawater. In the
Okay.
second summer, what we did is we focused on molecular modeling and selecting organic compounds that maybe that can be used as precursors to organics that may be present in seawater. So what we did is we selected simple molecules like formic acid, acetic acid, ethanol, methanol, formamide, and I forgot what the last one was. There was one more organic molecule that we selected that I can't think about what the name is right now. But we selected these simple organic molecules in an attempt to understand how they influence the reactions that are occurring at the anode, right? So we focused on the cathode, the hydrogen evolution reaction. In the second summer, we focused on the reactions that are happening at the anode, the oxidation reactions. How do these organic molecules affect the oxidation? How do they affect, for example, the chlorine evolution reaction, the hypochlorite evolution reaction, the oxygen evolution reaction? Or do these molecules undergo oxidation themselves? Do they generate other organic compounds as a result of being present in this solution? So the second summer was focused on molecular modeling and understanding the organic transformations that are occurring at the anode. When we came back from that experience at PNNL, we focused on purchasing an NMR, nuclear magnetic resonance instrument, so that we can, we were hoping to characterize the organic transformation. So if we introduce, for example, ethanol at the start of a reaction and we perform the electrocatalytic conversion, do we see something else, right? Is ethanol converted into something else? And what that would do is that would help us to understand, well, maybe ethanol is interacting with the surface. And if ethanol is interacting with the surface, how is it affecting the ability for water to interact with the surface? How is the ethanol interacting with the surface affecting the ability for chloride from interacting with the surface? So again, we focused basically on the electrochemical profiles of these organics while we're at PNNL. But when we came back to Guam, we were interested in saying, okay, if we introduce these organics, do these organics change? Can we
Mm.
identify what type of changes occur for these organics? And again, what that's going to help us do is build up on understanding fundamentally what's happening at that surface.
Well, the research and the project that you're doing, how close or how far away, I should say, do you think you and your students are from application? Like after X or more years, do you think you will be at a place where you would have understood or discovered something that can now be go from the realm of just pure research to applied or something that can eventually be productionized, if you will, in terms of um, new technology or uh, new energy source kinds of applications. How far away do you think you are from that?
So it's really hard for me to say that because I'm right now the science on Guam is fundamental, right? We're just trying to understand
Yes.
what is happening at that electrode surface. To scale that up to actually be using seawater to produce hydrogen for fuel, again, depending on what type of investments we can get, to scale up the technology, because the technology is there. There's a lot of places that are using novel electrodes to generate hydrogen from seawater. But again, those electrodes can be quite expensive. Though those systems can be quite expensive. So, we are at a fundamental stage of our research. We're trying to, again, bring the technology to Guam. That's one of the goals, is bring the technology to Guam and Micronesia. So make it something relevant here, but also expand the science so that we can publish, we can put out the information that we're getting here on Guam, because again, we are surrounded by seawater. We don't run out of seawater here on Guam. A lot of locations, they have to make trips to get seawater. For example, at Pinanel, they were asking us to bring our seawater out there because they would have to go
Yeah.
to Washington State, or I'm sorry, to for example Seattle or the west, or to the West Coast, in order to get seawater. So we were asked to bring some seawater, and we're not limited to that. We're limited to do we have the infrastructure to advance the science? Right now, we're at a very early stage in understanding, how our water interacts with the electrode, how the organics in the water around Guam interact with the electrodes. So one of the projects that was mentioned earlier was one of the students that I was working with. She was actually tasked with collecting water around different locations on Guam, and just running running the experiment on it, running the electrolysis on it, and then investigating whether or not, based on where she collected the water, at what time she collected water, was the water different, right? And we observed that there were some slight differences in the water. So with respect to location and time, there were slight differences. There were different profiles that we saw when we ran electrolysis on the seawater that may at some point be important if we try to upscale this technology here. So again, we're really at that fundamental level. I can't really say, in 10 years we're going to be moving to production of hydrogen and so forth.
So I'm playing devil's advocate with you right now. So what I heard was that you could upscale your research, you could upscale the technology. It's a matter of capital and specifically capital applied to more advanced electrolysis equipment and some other supporting equipment that if you wanted to fast track a productionization, if you will, of hydrogen as a fuel source. You could do that, but it's a matter of capital infusion specifically for more advanced electrolysis
Yes.
equipment and other things.
Correct. Yeah, definitely. The technology is there. The technology is definitely there. I mean, there's also a question on why don't we just purify the water, right? So why don't we just desalinate the water and then use purified water? That's another option if you wanted to generate hydrogen, right? Is take seawater, desalinate it, remove the salt content through osmosis, and then use it, as a purified feedstock. And that's another technology that can be used. And again, there's a lot of ways to use hydrogen as fuel, and it doesn't have to specifically come from seawater, right? You can desalinate seawater, and again, that technology is very mature as well, right? Desalination technology is very mature.
So the students who've been blessed to work on this project, how have you seen the way that they maybe have changed their viewpoint of their careers and Guam's role in clean energy production? Do you see a change in them in terms of um, seeing themselves as a part of, like you said, this hub of science here in in Micronesia that's going to produce these kind of results that might be able to be implemented later on down the road?
So I think one of the biggest impacts I've seen on the students here at the University of Guam is being able to participate in research at a national laboratory. It opens up their eyes to see that they can contribute, right? So a lot of times the students coming from Guam, they think that they're not of a caliber to operate in an environment like a national laboratory, right? So they sell themselves short. They say, okay, when I graduate, I'm going to do this, or I'm going to stay on Guam and work here. Versus when I graduate, I want to go to this graduate school because at some point I want to work in this laboratory. I want to be doing the science that these scientists are doing, I want to
Mm,
work on the science that these scientists are working with because I worked with these scientists before. I know what they're doing. I know the caliber of scientists that they are, and I am that caliber of scientist. So that is the one of the biggest things that I've seen about my students, is when we go out there, they work with these scientists, they see the caliber of these scientists, and they tell themselves, you know what, I'm at the same caliber, or I can be at the same caliber. Right? Coming from Guam, I'm not limited to what I can do. I know that I can go to graduate school. I know that I can be successful. I know that I can I can work on the science that can transform the nation, or that can transform my community. So again, that is one of the main things, one of the main goals that I have for this project is not only working on the science, but it's transforming the mindset of our students here to know that, they they have the potential to be these great scientists that they read about in the textbook, these great scientists that are making these changes, in our understanding of science. So that is one thing that I hope that the students who may watch this podcast get from, and the students that I teach every day in the classrooms here at the University of Guam, that they understand that they are the scientists that they read upon in these books.
outstanding. Yeah, that's powerful when you think about it. So if you were king for the day,
Mhm.
what would you do to basically upscale what's happening at UOG already, particularly if you're having that kind of impact on the vision and the way that these students are seeing themselves through this kind of participation? What would you do? What kind of partnerships would you do? What kind of equipment? What kind of different things would you do to kind of upscale what's already in work right now?
So the biggest thing that I would, if I was king and I could make a change, it would be improving the infrastructure for research at the University of Guam. Right. So the infrastructure of research at the University of Guam is not anywhere near what the capabilities are in the U.S. Even at not even an R1 institution, right? So even a lower ranked institution, we don't have the facilities, we don't have the support in order to do that type of research, right? Um, you know, for example, when I got my grant, it took me 1 year for me to get a research space. So I got my grant,
Mm,
I had the grant, I just wasn't given a research space, right? So
wow, it took a
so
year.
it was kind of depressing for me. It kind of made me feel like, wow, you pushed me, I was pushed so hard to get this grant, but yet once I got the grant, nobody wanted to give me a space to do the research, right? What am I supposed to do with this money? How am I supposed to make
Right.
progress if I'm not given a space, right? So,
Right.
it came around. Oh, we have no space. We have no space for this. But I'm bringing in, $1 million
Bringing
worth
in money,
of
yes,
grant
and
money.
research. Yeah.
I'm pretty sure we could find some space, and it wasn't until I would say, you know, within the with the prior to the second summer, I got my research space. So after the first summer, after the students came back, we didn't have a research space. Basically, we were just doing literature review the whole time. And I really couldn't make
Mm,
progress in that first year. And it was really depressing for me.
mm,
I was like, what am I supposed to do? I can't force myself into a lab, right? Because other faculty worked hard for that lab. So
right.
so I think the biggest challenge that the University of Guam has is providing the space for researchers to make the progress that they need, right?
Yes.
Providing the facilities,
Yes.
providing the infrastructure, providing what we need to make to make the difference that our community needs or expects us to be making.
Okay. Well, following along that same line, okay, as we kind of bring things to a close here, what's your ultimate and takeaway message to students, to funders, to decision makers who might be listening now about what you're doing, the prospects, and suggestions for the future?
So the main message I have is believe in the potential for renewable energy and alternative energy technologies, right? So again, believe in that potential, but the potential of these technologies to change our energy infrastructure, right? So there's a lot of times we talk about, oh, we want renewable energy, we want these alternative energy sources, but nobody really stands behind it. It looks good on paper, it looks beautiful when you talk about it, right? Going from 100% reliance on fossil fuels to 0% reliance on fossil fuels, right? That's amazing to talk about. But is there a real belief in the potential for these technologies to displace fossil fuels? And unless you have this true belief, you're never really going to get 100% behind it, right? And then another thing I want to say is invest in UOG and our students, because every
Yes.
day we strive at the University of Guam to innovate in order to improve the lives of the people of Guam and the people of
Yes.
Micronesia, right? So that's our job. Our job as a university is to innovate in order to improve the lives of the people of Guam and improve the lives of the people in our region, Micronesia. So that's where we come from as faculty. That's where we come from as an institution.
Wow, Doc. Thank you for your incredible insights. This was an amazing conversation. I was geeking out with all of the technical talk. I enjoyed that. Your passion comes through here. And it's really a powerful reminder about, you know, how we can build an innovation ecosystem when our students, our faculty, academia, business, government, federal government all work together to kind of uplift, things of need. So this was really great conversation. Thank you so much. Thank you for being a guest on the Innovate Quam podcast. Um, to my audience, thank you so much for listening in. I hope you all learned something today. I certainly did. Remember to follow me on all social media platforms, including Substack. Be sure to like, share, and subscribe to stay up to date on future episodes. And don't forget to check out my Innovate column in the Pacific Daily News every first and third Friday of each month. See you next time. And remember, whether you're at work, at home, or at play, always innovate. Thank you so much.
Thank
All
you.
right.
Have a great day.